Okay, so far we have discussed the topics on any aircraft, any part, any machine element, any substructure element that actually undergoes to only static loading. Now, I want you to think if I got a structure that's only going to static loading, the only way we discuss this that can fail is because probably has some flaw of some kind. Now, think about this. I got a structure. I like to use my small airplane, and let's suppose, but this is what I do. I design planes. So when you have this airplane, and now I want you to think this structure is going, this wing is going up and down, up and down, up and down, up and down, right? It's going up, it's going down because there's vibration, it's constant vibration, even if it's very small deflection. Those vibrations over time accumulate, and if there is a flaw, that particular flaw is going to keep growing, is going to keep growing, and that's dangerous for us. You can think about the machinery, think about the shaft, the shaft of your car. If the shaft is a very tiny crack on it, it can break. There's the plates of your car where your rotor discs, sometimes your discs, your entire braking system rests upon. And if there is a small crack, I've seen that person are taking the car to the shop and they have come up with, hey, the problem is just a brake, it cracked. So the problem with having a crack is severe and is significant, and we need to learn how to deal with it. The intention here is by no means to make you an expert in the topic. Here in the topic of fracture and fatigue, we can spend probably close to 3, 4 courses at advanced level and will never be done. And still, this is a big area of research. Is constantly there is research done there. There is testing done in this field to try to figure out what happens with each one of the phenomena. Okay, as an introductory discussion, let's consider this case. So this is a microscopic crack that's seen through a microscope, and you can see there's a crack that you cannot see at a glance. However, when you come on this side, as you can see, now you can see there's a big crack that happened on this big column, and this is a very significant crack. It started with something very microscopical, very small that you could barely see, and all of a sudden it cracked the whole thing. You could think about maybe a pipe, right? You got a small crack there, and you got a fluid that's flowing inside, so that over time that's going to bust, right? It can be. This is more a pressure type of pressurized uh, tube. Think about something like a bicycle, right? This is a bicycle frame, and you can see how this bicycle cracked. So this type of the presence of crack is significant. Let me give you some examples of aerospace structures. These are frames and spars. This is a spar of one of the spars. So this is a rib of a wing, and you can see how the crack actually has damaged this. So crack plays a big role and is very important to understand. And you can also see how the crack actually, many times the crack tends to just, if there is a tendency, there is a stress concentration somewhere, the likelihood of the crack initiating and breaking you through that uncertain that stress concentration field, right? That void, that's the likelihood of the path of the crack. So now this is a real picture from Cessna, by the way, uh, and this is the right wing of a Cessna. So this is really happened. So now, if I was going to tell you, you'll be amazed how many times that our airplanes fly and they can have some small tiny bit of cracks. It's not about you to look around the window and say, "Oh boy, there's a crack there." No, if you see the crack and from your window, then probably you should be scared to death and do your prayers because probably that plane is going down and fast. Or if you're working in a roller coaster ride and you're able to see a crack in one of the trails, uh, you one of the poles, you need to start worrying about it quick. Um, Now, we design planes, we design structures to actually have some crack, even if it's a microscopical level. It can be a tiny, 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 tiny small, and it can grow up to a certain length, after which it becomes a big concern. So, because just they're too expensive to be replacing these parts constantly, right? Um, so for this, we got several things that we can do when we study, when we have a presence of crack. There are different ways we do this. First is static loading. Okay, you are welcome to pause this video and take notes. Do you study what we call fracture mechanics? In fracture mechanics, we want to know if I just apply a static load, mainly we got fatigue, fracture mechanics as well, but that's comes under fatigue. This is static loading, okay, pure static loading. So if I have a structure, whatever the structure looks like, okay, and it has a tiny crack, the question is how much, and I got a certain load P, can I keep applying this load P and still be able to apply, keeping this crack intact so it will not grow? Okay, so in other words, the question we are trying to answer is, can the structure operate with a crack? And this is the basis of linear fracture mechanics. Will be the first topic that we will discuss, and this is the end of chapter 5 of your textbook. And then the other segment that we care for is fatigue analysis. Now, in fatigue analysis, what you're doing is you are taking some load and you are saying the load now is completely cycling, and the load is cycling over a period of time. And in reality, when you see this, it really doesn't happen like that at all. We are talking is it's completely random, right? Your loads actually look something like this when you do your real test data. So what we do is we take all this, we say, is there a way I can fit this nicely somehow, in a nice form, so I can approximate that, right? And we just do some sort of an approximation, and then we come up with a nice, beautiful cycling load like this. But there is a lot of random vibration that goes on in this type of analysis and study that actually also takes place. So in this case, the question is, will the crack grow with the load cycles? With the given load cycles, will this grow? So with this, what we want to do is we want to develop what we call SN diagrams. SN diagrams, in a rough sense, basically tell you if I have a stress, if I have certain stress, okay, for that particular alternate stress, this is alternate stress. So we are talking about this amount of stress, this alternating stress. Given that alternate stress, what is going to be the life of my structure? Okay, so in a nutshell, this is what we are trying to answer, we are trying to find. Now, the Goodman theory just tells me if my design point failed. Okay. This is what the Goodman or Gerber theories would tell you, the two most popular and typical failure theories that we use. This concludes our introduction to damage and fatigue tolerance.